Hi. Today we're going to talk about making decisions from both a cost and a technology standpoint. So we're going to look at some of the basics. The objectives for this material are to make sure we understand the basic decision-making process, make sure we're all on the same page there, identify the appropriate methods and tools for analytic and qualitative decision-making, and demonstrate application knowledge for the more common tools and methods. Greetings. The notes will be, of course, the course material will be fairly self-explanatory. NASA has a good systems engineering guidebook, and some of what I talk about will come from there, specifically section 6.8 on decision making. There's course materials, various URLs. I've also included a paper that I had written up for a conference, and it reported on work I had done on the F-14D instrumentation system. It's a Navy fighter. It was the last generation of this particular aircraft. And it's both flight and lab concepts, some of the decision making that actually went on in putting these systems together. Suggested reading: you don't have to buy this book by any means. However, if you have the Systems Engineering Management book by myself and Ben Blanchard, 5th edition, it would be in the review of section 9.2. All right, well, let's get started. We're going to look at models in decision-making, kind of overview. Then we'll get down to the various matrices and methods, decisions under certainty and uncertainty, and decisions under uncertainty that's probabilistic. So let's get going first with just a good overview. All right, we can classify models for decision-making in these 4 ways: physical, analog, schematic, and mathematical types. The physical type looks like what it represents. When we were younger, some of us put together miniature styrofoam globes of the solar system, and so that's a physical model. Scaled down, of course, but an analog model, it behaves like the original, but they're often meaningless from a visual standpoint. This could be something like electrical circuits that are often used to represent mechanical systems, especially fluid dynamics, flow of water, the flow of electrons, the idea of capacitance, and things like that. Schematic: these are graphical representations of a situation or process, such as a football play diagram on a blackboard. Mathematical: they symbolically represent the principles or situations being studied. Ohm's law or Newton's law of motion, things like that. And here's an example of the analog model, because the analog model sometimes seems to confuse a lot of folks. So a mechanical network diagram of a simple resonator, which is up on top, and one of the electrical network with an equivalent structure and behavior on the bottom. Again, you might see the flow of electrons, the capacitance, the resistance. All of these things are similar between the two, at least at a certain level, and can be described. Of course, they can be described in mathematical structures as well. Now a word about models and simulation. So models are the process of simulation. Models and the process of simulation are used to obtain factual information about a proposed or existing design. And these are often done on components that are being designed or system designs. The component design, you're down to components, and you can actually build prototypes, test them, modify them, and modify the design based on how these prototypes perform. Now, systems, what you want to do is you want to model the system, or rather a large part of the system, and make your decisions from that. And we'll have examples of those. For example, say an aircraft. Direct experimentation for the aircraft or instrumentation would involve constructing a full-scale prototype to test under flight conditions. And this is certainly done, or has been done in the past. It's extremely expensive and very time-consuming. You might build a full-scale model, to check size and space and things like that, and you might even put it in a wind tunnel. But again, very, very expensive, very time-consuming. Indirect experimentation, or even simulation, that's where you build several models of the aircraft to test different configurations, say in a wind tunnel. So you might, build the wing section or the fuselage or things like that. And of course, these models, this type of model has to be validated, but that's a topic for another class, for another day. So here's some examples, further examples of this indirect experimentation, if you will, this building sections. And these are actually sections built to prototype, well, sections built to scale. This one down here was it's a part of the test stand. It's just the fuselage portion of the F-14A, but it's built to size, so a pilot could get in. All of these areas are places where you'd actually have space in the actual aircraft fuselage for different things. This is the other parts of the aircraft. As I said, we're modeling different parts for different reasons. This tended to be for size. It also allowed a facility that could be, with the radar in front here, could be used for tracking. So a number of electronic systems could be modeled and simulated. Here, this is a mock-up of the whole aircraft, the aircraft engineering mock-up and manufacturing, called the EMA. These are for the A, but for the D version, which is what I worked on, we did the same things. And here you make a mock-up to test out all sorts of things. You want to make sure that you have the right kind of cabling length and cabling type and location of cabling that runs through the aircraft. You want to make sure that you have boxes in the right place and structural integrity, and you might take out sections and put them in a wind tunnel, once they were actually covered and things like that. So the thing we just looked at, that kind of front fuselage, here's a drawing of it. Yes, a schematic, you might say. Pilots could sit in here, the radar systems here. There are a number of different units, electronic units, that handle the different buses, help control the interface with any weapons. There was a missile test stand where you might have Sidewinder or Phoenixes or whatever, and they would actually plug into the fuselage, just as the electrical interfaces would be just as on the aircraft. Naturally, it's not quite the same physically. I mean, the cables are going to be laying on the ground here, and in the aircraft they'd be in the wing, that kind of thing. This EMA, then, this frame, it's difficult to tell, but this little window here is, you would push this out on tracks so that the radar would be out in the open here, and it could scan and look out over the Pacific Ocean, and test aircraft would fly by and it would track it, or what have you. There was a test stand, an instrumentation interface assembly that interfaced with our model here, with our prototype, and it would run, it would decode and demodulate various instrumentation on the aircraft and simulated signals of instrumentation and run them to computers. I think we used butterfly computers at the time to try to pull off real-time data and analysis. And this assembly had a number of instruments on it. And here's an example of one of them. I think this is the tape deck. To handle all of the instrumentation that came off of the prototype. One of the many benefits of actually doing a model or a simulation, regardless of the type, is that you have it for future reference. You can go back and when changes are made on the original design, you can test them out again and again, and you'll have a set of legacy data that you can use to verify and validate. So here's an example of, say, a process that's been a schematic that's been, that's one of the model types we could use. This was out of that effort and other efforts. It's how instrumentation systems for mil-aero systems are created. It was important to actually identify a process at the time. And as you would expect in this life cycle activity, you define requirements. There's a documentation path, part of the systems engineering activity. But you further take these requirements, define the functions, the electrical system, mechanical, and certain types of commercial systems. The functions, if you will, the implementation, how they interact, and then how the system is tested, is validated, and then finally ready for program support. So I thought it might be interesting to at least consider as a thought exercise from the F-14 aircraft example, just go back and identify the physical, analog, schematic, and mathematical categories for this particular example, and also indicate which of those, in the way that they've been shown, might be a direct experimentation model or an indirect one.